So good afternoon, everyone. Very happy CPS seminar speaker. And University of Pakistan. For all the interesting aspects of skiing and computer theory, and recently also discovered topics like deep learning. I did world class expert on heavy operators and the holography. Today, talk about very special.
Thank for hosting me. Really thanks for really great. The work that I want to talk about today is trying to develop a systematic order of any kind of operators based on the statement just to say what is the idea, if you think about ADA-CFT, ADA-CFT is a claim that actually the Hilbert space is the CFT equivalent to the Hilbert space of string theory. Now, this has mainly explored in the planar limit of any rules theory with ability and remarkable results. But that corresponds to the excited states of a string. That is very interesting, but there's much more than that. For example, we know that there are giant these are three brains, spherical topology. And apart from that, we've got black holes, we've got other space-time geometries. So there must be states inside the CFT space that correspond to these brains, active brains, new space-time geometry. To get both of those operators, you need to go well beyond them. You need to study every operator. What do we mean by the operator dimension? The dimension of your operator is this will correspond in state giant. Or you might study operator. This will correspond to So these guys with delta of order n squared, the operators which you call to black hole microstates, for example. I tell you that's the bare dimension. Remember that each field has a dimension of order 1. I'm studying composite operators that are constructed using order n fields. An enormous number of fields. Because you've got so many fields inside the operator, there are a number of difficulties. I want to point out 3 really crucial obstacles. The first obstacle is that there are finite n. What I mean by that is, if I was, for example, to start taking traces of matrix somehow, traces in K, 1, 2, going up all the way up to n, all of those traces are. As soon as you go above it, so if you, for example, take trace of P, n plus P, any positive P, this can be expressed in terms of the trace. Traces by the eigenvalues of n, and when you've got order n squared fields, you are going to have traces inside there with more than. Those can be rewritten in terms of traces with multi-traces with fewer fields in there. So it becomes a question of how do you even write down a set of operators that is not done. That's not. The second thing is that not planar. And what I mean by that is we're used to think in the larger limits, There's the top coupling and there's 1 over n. And to capture the large n limit, all you need to sum up the planar diagram. For these operators, that's not true. If you were to add diagrams with 1 handle for topology of course, it is a 1 over n squared separation. But here, the number of fields depends on n. If you count the number of planar diagrams, the number of genus 1 diagrams, genus 2, all of that becomes n dependent. And the number of say, torus diagrams is just so much greater than the number of sphere diagrams that you completely overpower the number of sphere separation. So if you're just going to some planar diagrams, you are not going to get a very large n. You have to be much more planar diagrams. And then the last thing, this, for example, plays a crucial role with is that if you were to calculate a 3-point function, let's say we take trace d1 normalize each of these so that they are large n. In this 3-point function, it's only non-zero, a is a1 plus b. And when k1 is equal to k2, when k is equal to k1 plus k2, the answer is k1, k2, k over. What this suggests is k1 and k2 and k are themselves all of order of n to the 1/3. In this 3-point function. The very big mixing double trace structure, the planar limit, the k1, k2, and k are order 1. This side vanishes, you don't get any. It's going to get very complicated multi-trace structure. So the kinds of operators that we're going to write down will be a lot more write down. To really start studying finite n relations if you want to take into account, but not just some of the planar diagrams. It's going to be a very complicated operator. It's going to be a very complicated multi-trace structure. Okay, so there is a thing. We're going to study heavy operators. Using the symmetric group dilatation. I'm going to start off by studying just a single matrix and develop the formulas. Then we will generalize more than one matrix. This comes from Earth. Okay, you always think. So integrability holds in the planar limit. When you go outside of the planar limit, you can study situations where we say have open strings of strings. There, the world sheet theory of the string is definitely not good. And the reason why we know that is that the kinds of boundary conditions you put on world sheets, verb integrability are rather restricted. What you need is you need the excitation of the world sheet to hit the boundary and reflect back perfectly. In most of these cases, when the excitation hits the boundary of the world sheet, some of that momentum leaks off onto the brain and it's not reflected perfectly. So all of the things that have like perfect reflections and so on, no longer occur in the operators. General, don't expect it. For black holes on physical grounds, you wouldn't expect it because they're meant to saturate some sort of Hales bound. So you'd want maximal mixing in the phase space, integrability with charges pushes the phase space up. So they really are a constant. I would say away from plane and go to spectrum. So this was done by Kirby. Just dealing with a single matrix, we'll see that this really gives all of the crucial ideas needed to the general. That paper. I'm going to be studying symmetric group, so let me just spell out my notation. I'm going to be using cycle notation for permutations. So, for example, this would be an element. This symmetric group is six objects to use it. This permutation on the second object, third, fourth. If I have to, I'll get this. So all you do is look at where you are. If you want to know what you're going to get, X number here. If you're at the 3, you're going to get the 1. So back again, 5, 6, 4, down. Now, let's talk about this. That gets ND. Day 1. And I will also have a permutation. I1, okay, 1, and so what's the now we see we're gonna struggle because we've got single traces, multiple traces, and everything else. Yeah, we've lifted everything into this space. In fact, if you write down the trace of sigma, e tends to n, and I mean by this, sigma times j, with this sigma and this sigma. This way of thinking about things is a very nice unit. So let's study that in this case. Then what you can see is you can take this sigma to write out what this gets the delta function is, how the map acts. This particular sigma, what this is equal to, trace of z, trace z, trace of z. Is these colors here simply reflect the permutation inside. Let me put the 4 in on its own. So now, any multi-trace can be written as a single trace in this bigger space of these tensor n. So we've got a unified language to talk about all of these traces. But not every permutation labels. So if I'm taking this, sigma is equal to 4, 5, 6, let's put 1 on its own, let's put 3. This is going to be exactly the same gauging variable. Inside the first trace, we'll be tracing the first C, the second C, and the third C. In this case, we'll be tracing the fourth C, the fifth C, and the sixth. But you can swap these, and that's a symmetry because of bosonic. So not every permutation corresponds to a different gauging operator. Cycle structure specifies a conjugate class. So it turns out that every conjugate class labels gauging variable. This is fine to make that. Think about the usual transform. So in our Fourier transform, e to the I k dot x is going to be all of that 8 by the character represented R. And the reason why this is a good idea, probably the idea of x that you use in our complete this kind of exactly goes, you know, for vector several one of the ordinal group and from elements S of sigma, so R and S different given by delta. And the second that stands for the number of elements. Then this will be 1 if sigma and rho belong to the same quantity distance loss multiplies with 0. So this is the completeness and orthogonality relation of the transform. Fourier transform itself takes this. Another n factorial, that's the order of the sigma is an extent. R of sigma, I to x, then we've got trace sigma. And you can see that we've gone from the permutations. So x, if you like, plays the role of k in that formula. The space is R is playing the role. Why is this? Well, the first thing is, what about the finite? The complete set of finite n relations are the statement that I are 0 whenever R has more than n. That is the complete set of finite n. There are no others, and as long as you R, the representation of the selected group, that means it's a Young diagram. All representations of Young diagram. As soon as the Young diagram has more than capital N rows, to a polynomial. That's the statement. All sure polynomials, most N rows, that's Z is capital N by capital matrix, absolutely. The one of the actual stable. So in fact, we solve all of the finite n relations. We managed to write down 6. Let's see how about calculating correlation. And place of 1 over n sigma is inside percent I R sigma. Okay. And what you can see is this thing over here, and this thing over here, R. Okay. One we are dimension. 4 R times like S is south. Another important property that are any permutation of a any. Finally, the trace of is simply the space to the distance. And this case, trace are the dimension of the space times the dimension of responding to take E tensor N. So this space can be decomposed into both reference and and both are labeled by a Young diagram. This is the result that's known as double centralized. What it says is, if you take N copies of vector space can be organized into representations of UN, and there's a certain multiplicity associated with that. That's given to you by the X. This Sn vector space is multiplicity. What this projected PR is projecting, it's projecting PR tensor. You take a trace of this, you're going to get the dimension of the symmetric multiplied by the dimension. Now, our next have the following: Ij, dagger, L. I'm dealing with U-N here. This is equal to delta L, delta. If we were to take the V tensor N, okay, down that N, out, what Wick's theorem instructs us to do, take every single pairing of the first N fields with the second product, and sum over all of those pairs. Now, it turns out that this can be written very nicely. How many pairings are there? N fields with N fields of vectorial pairings. And this is actually given by gamma as an element N and an inverse L gamma. This formula can be just by simply writing out this theorem. Now, I would like to calculate the 2-point function for got R E is dagger. And given by, I'm going to use this formula for the pure polynomial vector. I've got 1 over R S pure is dagger. Yep. Exactly. This is a character. If I plug in an element of the symmetry, if the character of that symmetry is a polynomial, I can put a tilde here. In both are written as basically because this guy is the character of the symmetric group. And this guy is a character of the unity group. So usually in math, you use the same symbol for both things. This thing, however, you insert an adjoint matrix. Here you insert an element. The now, if you look at this function, when we contract the z, and the upper index of the z goes with the lower index of the dagger, the upper index of the dagger goes with the lower index. So we now get sum over gamma goes over trace gamma inverse par gamma. That's not the planar diagram. That's all diagrams. That's all width. Now we use this fact that permutation is all new with the projection operator. Now we get 1 over r s. The sum just gives us an n factorial. Then we've got a trace s PR times ps. We know again by the projection delta rs rs factorial. The length of the trace PR is r. And we know formulas for the dimensions of these vectors. This is the answer to the first one. And we haven't just summed the planar diagram. We've summed all of the review. But we've done the sum using some projection operator. So we have indeed gone down. And then finally, property does. If you find a different thing, it's got all kinds of multi-phase structures. But there's some simplicity in all being organized. So the structure that you've got all of these multi-phases are arbitrary. It's reflective. For the single matrix, we've understood the structure of multi-phases with the finite end of matrix and written down of one set of operators, and we can go well beyond this. Now, this would give you the AES description of the object in a second. And when you start to study the very heavy operators here, you're even talking about giant graviton. And if you go to order n squared, talking about that. So the sure polynomials of that we go to the description of the what operator first, what from the graviton correlated to the background, there's the graviton calculation. And you're going to check this very carefully because you're getting the correct operator. So the analytic geometries are actually known. So the kinds of things, for example, is you could calculate semi-classic, a giant graviton that lifts, say, a closed string or something like that. You would do that, say, using the Born-Calc action, the correct initial final states, and semi-classical calculation. On the CFT side, it corresponds to having two of these sure polynomials together with a single trace, evaluating that. Those kind of computations. That's right. So the equation comes up to the M theory. So, well, the actual the equation that you land up solving to get more than the so it's all linear and very nice. In this situation, there's no normal. You have to generalize this. And in fact, it's not generalize it. Going to imagine we want to construct our operator now. My here. And Z and 1 J n plus 1 J I n J. Now, previously, we knew or we saw that swapping fields of the same type doesn't affect the operator. And that told us that different permutations that belong to the same conjugate are corresponding to the series operator. What's the corresponding statement? We can still take a trace of sigma y in sigma will be an element of plus range. But now two operators will give the same get two permutations will give the same gauge variant operator if they're related. So the element of the group swaps these fields, swaps these amongst each other, and swaps y's amongst each other. In that case, sigma 1 and 2 is the same. We can project that this relation defines an equivalence. So in exactly the same way that you can define conjugates of classes, define classes of this equivalence. This way we define there are more restricted conjugates in classes than there are conjugates of classes. The two permutations have related find elements. And you can count how many restricted conjugates of classes there are exactly matches. Then previously find the Fourier transform to solve the finite gain relation. And the element of that Fourier transform was the character. So we're going to generalize generalization. Is here. The Young diagram of n constant. Then we've got a representation R from S, irreducible representation of Sn times R will have n boxes, S will have m. Now there's a we want to take permutations that are inside Sn plus n. We need to consider all ways of putting the y's and z's together to produce the gauge variant operator. To provide out by this symmetry, because swapping z's amongst each other and y's amongst each other is we've got both of these. When you go from Sn plus n, Sn with S more than once. So we need to this is a multiple. Solution. So here we're building our operators with point matrices. These are not all linear. Classically, all yes, it's one loop. Vast majority of these operators will pick up the normal. There can be some non-trivial dilatation operators calculated here, and some non-trivial spectrum of non-trivial. That's what we're doing. That's spectrum of non-dimension. That excitation is some of. If you think about N is equal to 10 moles, for example, which is where we could apply this, we would have adjoint scalars by I, with I going from 1, 6, the Z field of phi 1 plus I phi, and the Y phi I Y. Exactly. Yes. Yeah. Absolutely.
So I wouldn't say that.
Why would you say it can't work for ABJ? So what we can do here, we can calculate the elements of the dilatation operator. So there's no problem in doing that. And for example, if you pick some collection of operators, I can actually get a matrix of numbers. It'll be a Hermitian matrix, and I can diagonalize that. In the planar limit, in fact, you have nice integrability, even in energy force of the moles. Away from the planar limit, integrability will not help you. So in this, even as soon as you have operators with a dimension of order n or order n squared, you calculate the dilatation operator, you must sum non-planar diagram. And as soon as you do that, you're away from planar limit and away from planar. So you now need also so our current has a label R. We've got some representation of Sn plus S. And we restrict to a subgroup Rs of Sn times S. So we also need the subgroup label. And then the multiplicity label plays a role. I want to restrict the place. I'm not going to place over the full space R. I'm going to restrict over the subspace Rs. But I can actually pick the row label that I'm summing over, the column label that I'm summing over. So I can have a multiplicity label for the row index that I'm going to be summing over, and a multiplicity label column. And what you will plug in some element. It turns out that this character has all of the nice properties of the normal group. So it's a real generalization of the group. It still has a proportionality. So there's a Fourier transform that takes us from this space. It's like the trace basis, multi-space structure. And land up in the restricted basis. Now, this is a function of p and y, so this is the actual real. Okay, shall we sum over the full group? Or okay. And that's the character, that's the nice property. So, by the way, this became a game defined. And that projector is again orthogonal, again calculate trace. So that if you go ahead and calculate y dash. This is again an exact result.
get a delta function, so the Young diagram, or Young diagram, or mismatch, Young diagram, mismatch. Then multiplicity labels also have to match. And there's a number system here. And R, the factors in the Young diagram, and other numbers here. These are all very well defined numbers that you can read off the Young diagram. And that answer to things are summing up all, not just the things. So if we come back, if we get the right formula in relation, there's four formulas. Any of these it vanishes. And that is, there are no way. Next thing is, go beyond player. If you did the sum the data diagram, you sum every single graph. This is the answer. And then finally, this complicated multi-trace isn't arbitrary. It's maintained by the factors organizing. That's the story of the two fields. Now, as soon as you've got two fields in the game, you have non-trivial mixing problem, and you can ask what the dilatation operator would find. Because there is a short fundamental dilatation operator at the time for us to make this dilatation operator. Yes. Just to remind you, this sector, which is the Y and the fields, the exact answer to the dilatation operator. No, it's not, there's no framework. Here we with this client. What you get is you can evaluate what it is. You can get the numbers for one unit. What's next? Is constant. I'm not going to write out the potential. Matrix representation R representing the symmetric group element that swaps one and then one. Remember, one is where a micro if the swap is acting on Y and Z. Then we have our projection operator. Then we have a map. Where this map maps from? It maps from the Young diagram R of the block one box. That's the time you block one box. To the Young diagram T of the block one box. You need to sum over all possible ways of blocking a box. If the operator is labeled by a Young diagram R, if you drop a single box, you cannot agree with T
after dropping a single box in those two operators. So in fact, the mixing of one is very, you can only mix with another operator if differs in the case of a single box in the time. Then this is multiplied by a matrix boundary. And get that for careful. Independent, the diagonalized dilatation. What you found was Hamiltonian or exclusion that negated. You can ask if you study this operator in some limits, do you see some sort of structural drift associated somehow? And what structure might be expected, or we might be expected to do this. So you see it, the young diagram part, take a number of very long diagram part with three very long rows, very long, all of these lengths, n boxes, and this is projection. You do all the three giant, the three D3. Then I knock some boxes. And what remains after I've knocked off those boxes? This young diagram that we got. This is the young diagram. Or big young diagram. These three boxes will be thrown and assembled. So, for example, one way down, 4 boxes. Top row, box. So the 9 boxes here, 9 boxes. Very nice. And it has the symmetry of this problem. One symmetry that this problem has, these are the boxes that we remove the Y box. And something that you can just check for this operator that's constructed, as long as the row lengths are very different, this operator has a symmetry. You can swap the column and the row in the number of Y fields that live in the same. That's a symmetry of the column. That's it. You're actually studying problems where, for example, S3, S3, S3. If you're taking S9, total number of Y fields, you want to divide out by the symmetry. Both indices want to divide out by the symmetry. And this defines some double process. And it is exactly the same way you find characters groups. There are characters double process. And we want to realize we build some nodes. One node for each node. And then each of the Y's corresponds to the edge. For example, this is one possible drop. If you count the total number of edges, there's 9 edges. There's an edge for each of these Y fields. And there's a constraint that must occur. These edges have to be oriented. And at each node, the number of edges entering the node must be equal to the number of edges leaving the node. This is just a graphical way to represent the element. But from the string theory point, it is a very practical interpretation. What is node corresponds to a giant graviton. The world volume of the giant graviton is an S3. If you're on an S3, so that's some sort of a compact gauge group, then if you think about the Gauss law, it tells you that the divergence of E must be our density. If you integrate both sides of this over the world volume of the giant, and you try to use the divergence theorem for this term, this would give you an integral of E dot A, but this is over the boundary of the world volume. But our giant is a surface, so it doesn't have a boundary. That's this zero. Part of the world volume. That's the statement with the same number of strings that any. So after you diagonalize the dilatation operator in the sector, you actually see very explicitly brain plus open strings merging. And there's various checks you can do of this. For example, on the Adelaide plane, you can locate where these brains are. What would you expect for the lowest classical energies? Just be mentioning the length of the strings. As they're very energy back. That's exactly what anomalous dimensions are. Okay, good. So then I think what I mentioned, so apply this to different black hole states and things like that. Then you maybe mention actually what we managed to do in this case. So this looks very nice in these corners of our set. Get hold of anomalous dimensions. You can work at large. One thing that you'd like to do, you'd like to actually develop this in a 108. And so far, all of these formulas, the formula that I've learned is the take operator as well, it was obtained by something all written, not just. But somehow it would be very useful if you expand these. And what we want to do, for all these operators that are very complicated, you have all of these effects added in, we're trying to derive an integral. The reason why we want to derive an integral representation is that if you have an integral representation, you can start to do some sort of a saddle point. And by expanding that generates. That was the yeah. And if you want to know if you can integral representation, and this is logical. I think that we've really simplified the description of these operators. These operators that are brains. So I'll write this down for two brains, two long rows. And if you think about this from the point of view of UN theory, they're used to thinking that you can subdrive indices that belong to a row and to symmetrize indices. That's the logic that we want to try in dividing what this is a this length over here. Operator.
5 or 5, 5, 5 or 5. And this formula looks long, but it's very the same form. You can see the bottom of ij, the top is KL minus. Let's put two these together. The 5, these we have with the 5 bar and 5, these would correspond to the boxes sitting over there. Boxes sitting over there come from this thing. And the reason for that is when you expand out this exponential, you get 2 to the end, you get 5 bars and 5 to the end. If you do this down to the integral, that's going to symmetrize all of these disease. How can you do the integral? Let's go over the 5 bar and the 5 and the K will make sure that you symmetrize the Z's that appear in that first row with those ones. The 5 and 5 or 5, 5, 8. Then the Y's or the ones that we've done the Fourier transform with double coset, that permutation is the Z together with Y's, if the Y's are second break, then sewing up the indices correctly according to sigma, or it's putting any Y's attached to the first row correctly. This in thinking about what the symmetric group is doing when it puts these indices together. Find out if you want a large n approximation with operators or large n approximation, what would be in some that's what we do. Then maybe just one final last thing is I have seen these of these block operators. What all done was energy. What was there is you had to go from multiple operators will be out states. Now, the restricted words give you a basis operating diagram and also this Q operator with null states give you these potential black hole candidates. You can work out what the matrix elements for basis gives you some large matrix and diagonalized. That's something that now has taken all of the 5 in relation to the account, does it use some flavor diagram, and again the sure is taming the structure. I think that's also another
propagation rate. So I
So, the reason why is in the same way that the states into this, if you expand this Laplace series of P1 and P2, these are eigenstates of the one with the operators, the very heavy operators. The label for the operator is power P1 plot power P2 plot, that's the Venn diagram. Sigma of the other open strings. This would also be some eigenstates. The operator, the you operator with a CFT, definitely. So this curly plane straight line, they are just symmetrizing the indices. You can see in this Venn diagram, most of the work is symmetrizing the indices in the first row and the second. Both of these are order N. Order N in the row, order N in the first. All of that symmetrization is done by the graph. Exactly. Yes. And there are some grades. There is some
Question? Any question online? Then, okay,